Hello, my name is Gabriel Allen. This is my Physics Lab Report 2 video. Now, coming up is the first video that I tracked. It was a video of a tennis ball falling, and I will then analyze it in Tracker afterwards. The main objective of this lab is determining how drag and gravity forces affect the falling speed of both a slow and a fast falling object. Go ahead. Now these are screenshots of the tennis ball being tracked in Tracker, starting from the beginning, the middle, and then the end. The weight of the tennis ball was 0.057 kilograms and the diameter was 0.065 meters, and this was marked on the actual Tracker. And also the plane for the ball had to be rotated since the video could not be rotated. The next video is of the second object, the paper, being dropped, or the slower object. Alright, whenever you're ready. Go ahead. Now this is the Tracker data for the folded up piece of paper falling. The weight of the paper was 0.0045 kilograms and the paper length approximately was 0.0183 meters. Again, the axis had to be tilted and it also began from rest. This is a picture of the code for the tennis ball when it was dropped, and the real things to know here is that F net force on it was just gravity traveling in the downward direction, and this right here is a picture of the graph and what it looked like. Now this is a picture of the code of the tennis ball being dropped with drag included in the equation. Then the main difference here is F net, the force equation, is F force of gravity plus the force of the drag, where the force of drag is equal to the negative b, which is the constant of proportionality, which is 0.0008 for the tennis ball, times the speed squared times the magnitude of velocity. It also needs to be included that the time for the tennis ball dropping and starting was 0.4 seconds, which was found when the video data was analyzed and tracked. And this last part is a picture of the graph, which in fact is not very much from the graph of just the gravity. Now this is a picture of the Excel data with the original tennis ball data found in Tracker graphed against the gravity data found in Python and the drag model data found in Python. Now as you can see, for gravity and drag, both these models are very similar for the tennis ball and the found actual drop length. However, because the force on the force of drag on the ball was very low, the graphs of these two curves still end up matching up quite well with the actual found Tracker curve. The main difference between the gravity and the drag model is the gravity is accelerating slightly faster than the drag model overall. Now this is a picture of the coding for the folded paper falling with just gravity on it, where F net is just gravity. The main things to point out here is the start time is 5.46 and the end time is 6.29, which is a time period of 0.83 seconds. Now this next picture is a picture of the code for the folded paper falling with the drag force included on it, and the main difference here is now F drag is being added to F gravity to get a more accurate model, and experimentally the drag constant for this model was found to be 0.24. And following this is a picture of what the curve looks like. Now this is a picture of the Excel data that graphs the Tracker data versus the actual models. Now this first graph shows the Tracker data for paper against the model of just gravity. And as you can see, the Tracker data is way off compared to the actual gravity data, meaning gravity is not just a sufficient coefficient in order to determine a curve like this. And this second graph is of the paper versus the model that had gravity and drag in it. And as you can see, the drag model more accurately depicts how it's going to act, but because of how the drag coefficient was found, it seems to be in a straight line, which could be a possible slight source of error for this. Now the main thing to take from all of this is that drag is a very important factor for determining how an object falls. As you can see, for the paper, it made a huge impact on how the curve was supposed to look, and for the tennis ball, it did not affect it as much, but is still an important factor when determining things such as this. For what does it mean? The answer to this is that the model with drag predicts the terminal velocity, because the model with just gravity would mean that the ball kept on accelerating, or that the piece of paper just kept on accelerating. But with drag, that means it actually reaches a terminal velocity. Without it, it would just keep on accelerating. So for the what if portion, what if the piece of paper was thrown down instead of just dropped? Well, if thrown down, the drag model would still accurately depict the graph. It would still reach terminal velocity. For just the gravity model, it would keep on increasing and never reach terminal velocity. For the thrown down drag model versus the gently dropped drag model, the terminal velocity for the thrown down model would be reached faster. This is because the drag force resists it faster, and thus it would reach terminal velocity at a faster rate. Well, that is my video. Thank you for listening, and that is my video. I'm Gabriel Allen.